Hello everyone. Today we'll be discussing about super forces between multiple charges. That is superposition principle of force. Superposition principle, it states like this: force on any charge due to a number of charges is equal to the vector sum of all the forces acting on that charge, taken one at a time. So when we are going to take the charges, say Q1, and I'm taking Q2, Q3, like that, up to suppose we have Qn charges, then the overall force that Q1 experiences, that we can find out as the sum total of force between Q2 and Q1. Let us say it as F1 is experiencing the force, so I write F12. Then Q3 on Q1, the force would mark it as F13, and Qn, that is acting on Q1, and Q1 is experiencing the force because of Qn, that will write as F1n. Suppose the position vectors that represents Q1 on Q2 on Q1 is R21. Position vector from Q3 to Q1 is R31. Position vector from Qn to Q1 I represent as Rn1. Then the net force that Q1 will experience, so we can write it as F net on Q1 is equal to F12 plus F13 plus up to F1n. This can be represented as 1 by 4 pi epsilon naught Q1 Q2 divided by distance square R21 square R21 cap plus 1 by 4 pi epsilon naught Q1 Q3 divided by R31 square R31 cap plus 1 by 4 pi epsilon naught Q1 Qn divided by Rn1 square Rn1 cap. This we can write this, everywhere you can see the constant term 1 by 4 pi epsilon naught. Q1 is common, so I'll take Q1 here. Then in the bracket I can write Q2 divided by R21 square R21 cap plus Q3 divided by R31 square R31 cap plus I can write Qn divided by Rn1 square Rn1 cap. This one as a whole we can sum up this way: Q1 divided by 4 pi epsilon naught. Summation sign, if you use I equal to, you start from 2 up to n, Qi divided by Ri1 Ri1 cap. This we can represent. Here I starts from 2, here it is 2, this is also 2, this is also 2, 2, 2, 2. When I is equal to 3, then this will represent 3, 3, 3. This 1 will remain fixed in their own positions. So this is the mathematical way of writing the sum of all the forces that are acting on Q1. Here is the presence of Q2, Q3 and Q4, Q5, Q6 up to n number of charges. This principle we call it as superposition principle of forces. To make it more distinct, the diagram and make it separate from the writing. The main thing that you have to know is about the sum total of all the forces, how to do. Then you get a net force on charge, Q1. The next thing that you have to know is about continuous distribution of charges. When the charges are densely placed in an object, then we say that the distribution of charge is continuous. I'll write on the heading. Continuous distribution of charges. There are three types of distribution of charge. The first one, we call it as linear charge distribution. The second one is your surface charge distribution. And the third one is your volume charge distribution. Now let us see one by one, where do we get linear charge distribution and what effect or what is the force experienced by a test charge placed near a wire where charges are distributed linearly. So first one, let us take, there is linear charge distribution. Linear charge distribution generally it occurs in wires, straight conducting wire. Suppose this is your wire where charges are concentrated. A small portion of it, if I take it as dl. Now what force this dl will exert on a test charge, let us say it as Q0 placed near to the wire. To know this, we represent it in a three-dimensional pattern with x-axis, y-axis and z-axis. This is the origin. The position vector of the test charge, let us say it as r cap, or simply you can represent as vector, r vector, and the position vector of dl, let us represent it as r dash. Then the force that is experienced by dl on q0, let us represent it as r naught. Then if you use Coulomb's law, we can represent like this: the force F that is experienced by Q0 due to the presence of dl can be given as 1 by 4 pi epsilon naught Q0 integration of lambda dl divided by r naught square r naught cap. Or more nicely, if you write down, force F is equal to Q0. You can take it here. 1 into Q0 is Q0. 4 pi epsilon naught integration of lambda dl divided by r naught square r naught cap. This is the force experienced by Q0. This is the presence of linear charge distribution. Here dl is a small portion of the wire. That's why we are doing the sum. This is a line integral. Sum of all the charges in the wire that will be represented by lambda dl, where lambda dl is known as lambda is known as linear charge density. It is defined as charge per unit length. Its SI unit is Coulomb per meter. So now if you look at it very carefully, lambda is known as charge per unit length. Now I am using this dq/dl to represent small quantity of charge. In this region, small region, you have less number of charges, dq, and this length dl is also not the whole length. Write this dl, indicating the small length of the wire. Now here dq is equal to lambda dl. That's why in place of charge q0 and this charge we are representing as lambda dl, that represents charge dq. So this is about your linear charge distribution, that is in one dimensional. Now the second case, that is your surface charge distribution. In surface charge distribution, it is for two-dimensional. It is in a plain sheet. Suppose the sheet is like this, a plain tin sheet you can imagine, or an aluminum foil. Here the charges are on the surface this way. First we'll take a small surface. Let us write this as ds. In a plain sheet, here the force experienced F can be written as Q0 divided by 4 pi epsilon naught. Surface integration of sigma ds divided by r0 square r0 cap. This is the expression for force that Q0 will experience because of the presence of ds. Now this sigma is known as surface charge density. It is defined as charge per unit area, and its SI unit is Coulomb per meter square. So here sigma is known as charge per unit area. Here ds represents small area. Here also you have to do sum up. Why you have to sum up? Because ds is a small region. When you sum up, you will get for the whole sheet of metal. The third one, that is your volume charge distribution. In volume charge distribution, your diagram will look like this. This is your three-dimensional object. Suppose a small portion of it you took it, and this volume will be called as dV. Small volume, the whole thing is V, and the small one is dV. Here also the charges are spread in all the directions and all the region. This unit vector I am keeping the same, that is r dash. Here the vector will be r naught. Then in this case, the force experienced by Q naught because of the presence of a cuboid here can be expressed as force is equal to Q naught divided by 4 pi epsilon naught. Here volume charge density we write it as rho, and then the surface will change it into volume. In this case, rho is known as volume charge density, and the integration will be over the whole volume of the solid. It is defined as charge per unit volume, and its SI unit is Coulomb per meter cube. Here rho is equal to charge per unit volume dq by dv, and dq is so rho into dv. Here we are writing rho dv. That indicates the charge, and when we sum up the sum of all the charges that are residing on the surface of the cube. That is your second topic. Next thing that you have to know is about electric field. Here we have reached now field. Electric field, when you say, it is a region or a space around which electric effect can be felt. Suppose you have a source charge, let me write it as plus Q. This is your source charge, and if I take a unit test charge, suppose say plus Q naught, within this field, then this unit test charge will experience some force. The force will be force of repulsion. So we define like this: electric field is a region. It is a region or space around which electric effect can be felt. Here the field is because of the source charge, and the effect is felt on the test charge Q naught. And the next term we will have to know is about electric field intensity. Electric field, as it is a vector quantity, and we can measure electric field. The strength of electric field, we call it as electric field intensity. Now let us see. Electric field intensity is defined as the force. We represent with E with an arrowhead since it is a vector quantity. Electric field intensity is the force that a unit test charge experiences. This unit test charge, how much force it experiences, we call it as electric field intensity. With this formula, you can find out the strength of electric field, how much Q naught experiences because of the presence of other charge. In the earlier diagram that I have shown to you, the source charge is capital Q, plus Q I have written. Now let us find out the electric field due to a point charge. Electric field due to a point charge. Suppose this is your point charge Q. Now if I bring a unit test charge near to this point charge, then how much force the point charge will experience. Suppose this is our unit test charge and kept both are positively charged, so we all know that it will show force of repulsion. It will have some force. That force we call it as force of repulsion. If you take the unit source charge as the origin of our coordinate system like this, then you can represent this way also. So the unit test charge, the position vector, if I draw here, if I act as R as the position vector, then the force experienced by Q naught due to the presence of Q can be written as, using Coulomb's law, it can be written as 1 by 4 pi epsilon naught Q naught divided by product of the two charges divided by distance square, and in terms of unit vector you can write as r cap here. Now as we have learned, electric field intensity is the force per unit test charge Q naught. So this can be written as force value. If you put it here, then you will get 1 by 4 pi epsilon naught Q naught divided by r square r cap, and outside again divided by Q naught. This Q naught you can cancel it out and can get the expression for electric field intensity due to a point charge. This is the expression for electric field intensity due to a point charge. In magnitude when you write, this is in vector notation, in magnitude when you write, you will not put arrowhead and this r cap will not write. In magnitude it will look like this. In magnitude form, right, E is equal to 1 by 4 pi epsilon naught Q divided by r square. While calculating electric field intensity, we are using the formula like this. Now, this is electric field intensity due to a single charge that is experienced by Q naught. Let us see electric field intensity due to a system of charges. Electric field intensity due to system of charges. When I say system of charges, it indicates a large number of charges are present, and then how much this Q naught will experience will have the electric field intensity. Suppose this is Q1, here I am writing Q2, here Q3, like that, many more, suppose say up to Qn. Then already we know that Q1 will experience force on Q naught. Let us write simple as F1. The electric field intensity, let us write as E1. Like that, Q2 acting on Q naught, it will have force F2, and let us say electric field intensity as E2. Q3 acting on Q naught, let us say it is F3 and the electric field intensity is say E3. Qn acting on Q0, let us say it is Fn and electric field intensity is Fn. Then the unit vectors, if I take it as R1, and if I take it as R2, here R3, here Rn, then mathematically you can write the net electric field intensity experienced by or net electric field intensity experienced by Q0 will be equal to E1 plus E2 plus E3 up to En. And electric field intensity, as you know, is 1 by 4 pi epsilon naught Q1 divided by R1 square, R1 cap plus 1 by 4 pi epsilon naught Q2 divided by R2 square, R2 cap, let it do gone. Last one, if I write 1 by 4 pi epsilon naught Qn divided by Rn square, Rn cap, and this one we can write together like this, 1 by 4 pi epsilon naught, then with a summation sign, let us write I is equal to 1 up to n, then it will be Qi Ri square Ri cap. It can be written like this. This will give us the resultant or the net electric field intensity that is experienced by Q0 because of the presence of other charges Q1, Q2, Q3 up to Qn. Now let us learn about electric field lines. Electric field lines are continuous curves that are drawn so that tangent at any point gives us the direction of electric field lines. Like suppose it's a continuous curve I have drawn on line. Then any point if I take and draw a tangent to it, tangent is a line that touches at only one point. This tangent gives us the direction of electric field lines. There are two types of field lines we say in general. There is uniform field. You come across these two, uniform field and non-uniform field. When we say uniform field, then the field lines will draw parallel to each other. This will indicate a uniform electric field. Or you can draw this way also. Like this also you can draw. It will represent uniform electric field. You will write it as E. Like this. But if the field is not uniform, these lines will not be parallel. Some may be going straight, some may be going like this, some may be going like this, some may be going like this, some may be again going like this. So this type of field is non-uniform field, and this type of field we call it as uniform field if the field lines are parallel. These field lines for a positive charge, if your charge is positive charge, field line goes away from the positive charge radially. They go away radially. It is three-dimensional. Suppose if this is the charge, then the field lines will go away perpendicularly. in all the direction, down, down, this side, this side, this side, this side, all the side, it will go away. It will spread equally. On board it appears like two-dimensional, but in actual practice it is three-dimensional. They are all perpendicular at the point where it is striking. Here it should be 90 degrees. Like suppose this is the curve. If I draw a line like this, it must be perpendicular at that point. It must be perpendicular. So in a positive charge, the field line spreads uniformly in all the directions. It goes towards infinity. It starts from positive charge and goes towards infinity. When I talk about a negative charge, then the field lines will come perpendicularly inward. It will all come inward. From where it is coming, then you say that it is coming from infinity. It is coming from infinity. So if I keep a dipole is a system of charges, one unit positive charge and one unit negative charge kept close to each other, kept very close to each other. Now if I draw the field lines, then we know that positive and negative charge, they attract each other, so it will look like this. It comes from positive and goes towards the negative charge. It comes from positive and will go towards the negative charge. But you have to be very careful. These field lines, they never touch each other. It comes towards the negative charge. It comes towards the negative charge like this. Like this. From positive it goes away, and towards the negative it will end up. If you look very carefully, they do not form any closed loops. This field line that you can see is going from positive to negative, but it's not coming from negative to positive. It's still going from positive to negative. When you say closed loop, then it has to go from one end to the other end, and then it has to come back, then it will form a closed loop. So we say that electric field lines never forms closed loop. When we take two similar charges, as we know they repel each other, they will appear like this. They are pushing each other. So similar charges, as they repel, it will look like this. They will not come nearer. The high pressure region will be produced between the two charges. Here you can see as they are attracting each other, as they go towards the other end, they come closer and closer. But here as they go from one end to the other end, they diverge. They don't go closer, they diverge and go over the other end. Other side. Field lines can never intersect each other because electric field line gives us the direction of electric field, gives us the direction. Suppose two field lines happen to cross each other like this, suppose. Then at this point, if I draw tangent for this curve, it will be like this, and at this curve, if I draw a tangent, it will look like this. So two different directions will come out at the same point, which is not possible. In a field line, if you take any point, it must have only one direction. That's why two field lines can never cross each other. With this, we have come to the end of this topic 2, that is your Coulomb's law. Next topic, we will be discussing about electric dipole. For today, thank you and have a nice day.